This video is a review of torque and rotational motion for AP Physics 1. Early on in the school year, we learned that forces can cause an object to translate. And what I mean by translate is if I have an object at position A and I want to get it to position B, then by applying a force to that object, I can get it to translate. However, when we study rotational motion, we study a new quantity that is like force, but we call it torque. And similar to the way that forces cause an object to translate, a torque causes an object to rotate. So not move from point A to point B, but to revolve around an axis that is within the object. And the way that you generate a torque is by applying a force a certain distance r away from an axis of rotation. And so all objects that are rotating must be rotating about a certain axis of rotation. And in fact, a lot of rotational motion problems rely on our understanding of the axis of rotation or defining an axis of rotation in the problem. The generic equation for torque uses the Greek symbol tau for torque, and it is equal to r times F, where r represents the distance from where the force is applied to the axis of rotation, and F represents the force. And so for that reason, torques, which are symbolized by tau, have units of newtons times meters, or newton meters. When studying torque, we soon learn that the equation is a little bit more complicated than just r times F. The true equation could be or should be written as Rf sine theta. And this is because only forces that are perpendicular to this lever arm or moment arm, and when I say lever arm or moment arm, I mean the distance from the axis of rotation to the location of the force. So this here represents r if I'm talking about this force here. And so make sure you're familiar with the terms lever arm and moment arm as a way of quickly describing that distance, as opposed to always calling it the distance from the location where the force is applied to the axis of rotation. And so what I mean by only forces perpendicular to the lever arm can cause a torque is, let's imagine what's happening with this force here. Right, this force is being applied parallel to the direction of r. And so the way that I've drawn this picture, this white dot here represents the pivot point, and maybe we're staring at a little rod that's there on a table or something. If I apply a force on the end of the rod toward the axis of rotation, it doesn't rotate counterclockwise or clockwise. It just pushes on the axle, that point where the axis of rotation is. And so forces parallel to r, which for that force, r would represent actually the whole length of this rod, forces that are parallel to r can't cause a torque. The way that we generate a torque is by applying a force that is perpendicular. And so these other two forces that I've drawn on this left rod are perpendicular to r. You can see that there is, an angle of 90 degrees between the moment arm and the force. And that's how you generate the largest torque. And that's why when we want to open up a door, we push on it perpendicularly. Or if we want to open a cabinet, the handle is perpendicular to the door. It makes it easiest for us to open it. And so forces like that will cause a torque, but more importantly, for the way that I've written the equation in the top left, where there's an angle dependence, is if there's a case where a force is actually applied at some weird angle. And so here in this bar, since the force is applied at the end of the bar, the moment arm, that lever arm, that distance would be the whole length of the rod. But because that force is applied at a weird angle like that, only a component of that force is causing a torque, and the other component actually doesn't do anything. And so the two components of this force, so here's that force F at some angle. There are two components to that force. There's a part that is parallel to r. I'm going to call this F parallel to r. and there's a part that's perpendicular to r. I'm going to call this F perpendicular to r. And as I've shown on the left, a force that is parallel to r does not cause a torque, and that doesn't matter if you're pulling on it or pushing on it. If it's parallel to r, it doesn't cause a torque. And so this component of the force does absolutely nothing to help the rod rotate clockwise or counterclockwise. It's only this component, this perpendicular component, that allows that to happen. And so we can define this angle to be theta and say that the sine component of that triangle, the opposite leg of the triangle opposite relative to theta, would be the perpendicular component. And for that reason, in the torque equation, the true torque equation, we have Rf sine theta. So a couple things. If you ever see that the force is perpendicular to r, you don't have to worry about sine theta. But if the force is at an angle, you do need to make sure that you're finding the perpendicular component. Some of you might remember that there's a more maybe complicated, maybe not way of doing this, where instead of finding the perpendicular component of f, so finding the part of f that's perpendicular to r, in some cases it may be more valuable or more simple to find the component of r that's perpendicular to f. In this picture that I've drawn, it looks kind of complicated, but I want you to just imagine a scenario where maybe this skill might be applied. So in this case, the force F is exerted downward and to the right like that, and if I continue this line of force to angle backwards up into where I have all these words up there, I could also create a different triangle where I generate the perpendicular distance to this line of force. And although it's a little bit sloppy of a picture, I hope that you can see that the angle between the red and green dotted lines is perpendicular. I find looking at, for most of the AP Physics 1 problems that are asked, you can just look at the force and find the perpendicular component of the force, but in some cases it may be necessary for you to extend the line of the force back and draw a line that represents the perpendicular distance from the axis of rotation to the line of the force. And maybe you remember me mentioning this in class and me calling that, instead of r, we called that what this green dotted line would represent, we would call that r perp, or the perpendicular distance from the axis of rotation to the force. One little point that I mentioned at the bottom, which really isn't a review of rotational motion, it has to do with work as well, but just one thing to distinguish. In order to do work, a force must be parallel to the direction something is moving, and we have the equation W equals Fd cosine theta. So in order to do work, the force had to be parallel. The parallel component is what we cared about. And in order for there to be a torque, the torque has to be perpendicular, so not parallel, but perpendicular. And in this case, we get the equation torque equals Rf sine theta. And so in the case where we needed the parallel thing to do work, we have cosine. In the case where we need the perpendicular part in order for there to be a torque, we get sine. And so maybe it's helpful to remember those two equations at the same time, their similarities and their differences. If you study dynamics, where we talk about forces, we tend to categorize things as having balanced forces acting upon them or unbalanced forces. And now I'd like to do the same thing for torques. And so on the left-hand side, if there are balanced torques acting on an object, then the net torque will be 0 and the rod will remain at rest. And let's look at this picture to ensure that the picture that I've drawn has a balanced torque. Here I have a force F that is being applied at the very end of the rod. And then halfway through the middle of the rod, I have a force of 2F that is directed in the opposite direction. And maybe the length of the rod, the rod has a certain length, and maybe this distance to half of the rod is r, and the distance or the length of the whole rod is 2r. For that reason, the torque generated by the force that's pointing downward would be 2r times F, and the torque that is generated from the upwards 2F force would be R times 2F. And for that reason, those two torques are equal. I hope that you don't always have to write down the equation like that. Torque is equal to R times F, and since the forces here are perpendicular to R, I don't have to worry about the angle. But since the 2F force was applied halfway from the axis of rotation to the center of the rod, then you would have to have double the force to get equal to torque as applying a force at the end of the rod. So in that case, the torques are balanced. The forces are not. Notice how there's a 2F force going up and a 1F force coming down. The forces are very much not balanced. But the net torque is equal to 0. And therefore the rod remains at rest. And for the unbalanced torque case, and so here in my picture I have a force F that's applied at the end of the rod, and then a force F that's applied in the opposite direction but a little bit inwards. Since those forces are equal, the only way that the torques would be equal is if they were applied at the same location on the rod in opposite directions, and that's not the case here. And so the net torque is not equal to 0. And if the net torque is not equal to 0, then the rod will angularly accelerate. In the same way that if the net force on an object is equal to 0, the object will accelerate. If the net torque is not equal to 0, the rod will angularly accelerate. And maybe you remember the equation down below as Newton's second law for rotation, where instead of the net force equals mass times acceleration, we have the net torque is equal to moment of inertia times angular acceleration. So please remember that I represents that rotational inertia, or that moment of inertia. And maybe you remember that it's a quantity that's pretty similar to mass for rotational stuff. And I, which yes looks like a fish, is the Greek letter alpha, which is the angular acceleration of the object. And if you solve that for the angular acceleration, you'll see that if the net torque goes up, then the angular acceleration goes up. The bigger the torque, the bigger the angular acceleration. But if the moment of inertia goes up, the quantity that's like mass, if the moment of inertia goes up, then the angular acceleration will decrease. And after we studied torques, we learned about something that was a really important topic for studying all sorts of problems, and these problems were called equilibrium problems. After you study forces, you learn that one case for equilibrium is that the net force needs to be equal to 0. If the net force is equal to 0, an object will either continue along moving at a constant speed, or it will remain at rest. And so for that reason, the net force being 0 is a condition for equilibrium for a system or for an object. And now that we study rotation and we talk about torques, we learn the second criteria for equilibrium, and that is that not the net force, but the net torque on a system or an object needs to be equal to 0. And we talked quite a bit about these two criteria for equilibrium. And we said things like if the net force is equal to 0, then an object can't translate. It can't move from point A to point B. If the net torque on an object is equal to 0, then it can't rotate, right? And please know that an object can stay in place and rotate, or it can move from point A to point B without rotating. It can translate without rotating, or rotate without translating. So if one of those two things is equal to 0, the other one could still not be 0. However, if an object is in static equilibrium where it's not moving at all, then that means it's not rotating and it's not translating. Then these two conditions for equilibrium can be applied. And it doesn't mean that, oh well, it's equal to 0, these equations are useless. You might remember staring at pictures of like a ladder leaning against a wall, for example, and writing equations for net force equals 0, where we could take all of the forces that were applied on that ladder and set them equal to 0. And then similarly write equations for different torques that were being applied to that ladder, set those equal to 0. And we could take those equations and solve for things because these equilibrium criteria, the net force or the net torque equals 0, allows us to start writing equations for an object where there's forces or torques being applied. One of the reasons why rotation tends to be a challenging unit for students is because we tend to learn all of these things. We learn about kinematics, dynamics, energy, all these things, and then when we get to rotation, we study all of those things again, but for rotation. And so we kind of started off with rotational kinematics. We redefined every single quantity we learned about kinematics for rotation. And so if you have a solid understanding of kinematics, then when you start to look at the rotational kinematic equations, really nothing's different. Instead of the equation average speed equals displacement divided by time, we have average angular speed equals delta theta divided by delta t, right? Delta theta represents an angular displacement where theta would be measured in radians. And instead of average acceleration for linear quantities, which would be equal to delta v divided by delta t, we have average angular acceleration, which is equal to delta omega divided by delta t. So angular speed and angular acceleration instead of just velocity and acceleration or speed and acceleration. And similar to the three kinematic equations that we all know that's on the top left corner of our equation sheet, there are rotational kinematic equations, where if you look at each variable in the regular kinematic equations, we can substitute in the rotational kinematic equivalent to get the new equations. And the top two equations that are listed here are on the equation sheet, but for some reason, this third equation is not listed on the equation sheet. But you could just look up at the kinematic equations and look at the third one, and then replace all the variables to get it if you need it. In the bottom right-hand corner, I have a little chart that will hopefully help you remember the differences between these things. For translational quantities, we measure position with an x or a y, which is measured in meters, but for rotation, we measure things relative to a certain angle, which should be measured in radians. And hopefully you remember that sometimes we aren't given things in radians, and so we need to make conversions. And so maybe you remember that one rotation is equal to 2 pi radians, which is equal to 360 degrees. And so if you ever needed to convert from rotations to radians to degrees, you could take two of these quantities, any two of these things, and use them as a conversion factor to go from rotations to degrees or whatever you need to do. The translational quantity for speed was velocity, which was measured in meters per second, and for rotation we used the Greek letter omega, which is measured in radians per second. For acceleration, the units were meters per second squared for translational quantities, and for rotational quantities or angular quantities, we use the Greek letter alpha to represent the angular acceleration, which is measured in radians per second squared. And maybe you remember me saying that radians or degrees are a dimensionless unit where we write them in order to know that we know that the units are in radians, or that the degrees are being measured in, the angles are being measured in radians, but it doesn't actually factor into equations. And so later on in this video, I think you're going to see me write some units where the radians are there, but we don't actually write them in the final units. They're kind of like a placeholder. Earlier I talked about a quantity called the rotational inertia, or the moment of inertia. And now I'd like to talk a little bit more about that quantity. This red box here, there's a statement that I feel is incredibly important. Objects with mass distributed closer to the axis of rotation will rotate more easily. I think that if there's one thing that you remember about rotation, this should be it. Objects that are rotating can have different mass distributions. They can be hollow, or they can be solid, they can be like a disc, or they can be like a hoop. Or I could take an object like a rod, and I can have different axes of rotation. I could have an axis of rotation where the rod is rotating about its center. I can have an axis of rotation where the rod is rotating about its end. And so there are different ways to distribute mass, right? Mass distributions can be different. And depending on how the mass is distributed, we can figure out how easily an object is going to be willing to rotate. And what I'm telling you is that objects that have mass distributed more closely to that axis of rotation are going to rotate more easily, or maybe rotate or angularly accelerate at a greater rate, or have greater angular speeds, because of the fact that the mass is distributed more closely. It just makes it easier. There was one day in class where I had two long rods, and attached to one of the rods I had two heavy weights that were attached at the ends. And attached to the other rod I had two weights that had the exact same mass, very close to the center of the rod. And I think each one of you picked up both of those rods, the one with the weights on the ends and the one with the weights on the center, and if you grab those and try to rotate them, the one with the mass distributed closer to the center is very easy to rotate, and the one with the mass closer to the end is very hard to rotate. So again, the one with the mass distributed further away was harder to rotate. Closer to the axis of rotation, which is your hand, right? The axis of rotation is where your hand is placed at the center of the rod. It's easier to rotate. So, therefore, the rotational motion of an object depends on not just mass, but the mass distribution. And maybe you remember a great demonstration that we did where we put a disc and a hoop at the top of a ramp, and I asked you which one would make it to the bottom first. Now, there are ways that we can turn this into a very complicated conservation of energy equation, where we say at the top it has, some energy, and at the bottom it has different kinds of energy, and we write out some long equations. But as long as I know that there's a disc and a hoop which have different mass distributions, then I can tell you which one's going to make it to the bottom first. And so if I tell you that the disc and the hoop each have a mass m, so the disc has a mass m, the hoop has a mass m, and they each have a radius r, then what we could say is, for the hoop, all of the mass of the hoop is concentrated in the ring around the outside. And so if the axis of rotation is right there in the center, then all of the mass is concentrated in that thin ring of mass far away from the axis of rotation. Now, the disk does have some mass that is all the way on the outside of the axis of rotation, but some of that mass is closer in, and that's kind of like how a disk is defined, right? The mass is uniformly distributed throughout its size. Because the disk has some of its mass distributed closer to the axis of rotation, it makes it to the bottom of the ramp first. The disk wins. And so we've been fairly quantitative so far, but remember that the moment of inertia of an object can be written as a form of an equation where all of them have a mass times some sort of distance squared. A lot of the times for like a disk or a hoop or a sphere, that distance is the radius of the object, so r would represent the radius. But there's some instances where it represents the length of the object. For example, with a rod, it would represent the length of the object. So m represents the mass, and r represents either like the radius or the length of an object, and b represents a coefficient. So it's some number that is there that if I know that number, I can write the equation for the moment of inertia. So that's the general form of the equation, but whether I'm working with a disk or a hoop or a rod, I get a different equation. And so for a disk, the moment of inertia equation is 1/2 mr squared, and for a hoop, it's mr squared. And maybe you can relate that to the picture now. The disk has a moment of inertia of 1/2 mr squared, and the hoop has a moment of inertia of mr squared. The hoop has a bigger moment of inertia. And if the moment of inertia is the quantity like mass, then maybe you can reason that the hoop has more moment of inertia, more rotational inertia, therefore it's harder to get it to move down the ramp. And the last thing that I have here is a couple of moment of inertia equations for a rod. And the reason why I put these here is to help illustrate that if I have a rod and it's spinning about or rotating about its end, so this is the axis of rotation, then the moment of inertia equation about its end, which is this top one here, is 1/3 ml squared. But if I take that same exact rod and instead I spin it about its center, then the moment of inertia equation becomes 1/12 ml squared. And so not just the object and how the object's mass is distributed can affect the moment of inertia, but also the axis of rotation. It's important to know what the axis of rotation is. Now, when I'm rolling things down an inclined plane, the axis of rotation is always going to be the center of the object. But if I have a rod, I can choose whether it's the center or the end. And it should make a lot of sense to say that if I am holding an object, holding a rod by its center and trying to get it to rotate, that it's going to be a lot easier than if I'm trying to rotate the rod by the end. If you don't believe me, just take a long, heavy object and try to rotate it about one end, put your hand at one end and rotate it, and then put your hand at the center. It's going to be a lot easier when your hand is at the center. For that reason, the moment of inertia, where the axis of rotation is the center, should be much less. And we see that, right? 1/12 is much less than 1/3. When we study rotation, we also learn about a quantity called rotational kinetic energy, which we sometimes abbreviate as k-rot, for k-rotational, which is different from k-translational, k-tra, which we know is, of course, 1/2 mv squared. The rotational kinetic energy equation is 1/2 I omega squared, and hopefully you can see that instead of mass, I now have moment of inertia, and instead of linear speed, I have angular speed. And so, quite simply, the linear or translational quantities were replaced by the rotational or angular quantities. And maybe this manipulation will help at some point. Remember that, for translational, mass is just mass, but for rotational quantities, moment of inertia has an equation, b mr squared, where b is the coefficient and m and r represent quantities related to the object. And also there are a couple of really important equations that I have at the bottom of the screen which are not on the equation sheet. V equals R omega, and A equals R alpha. These equations relate the linear and angular speeds and the linear and angular accelerations through the radius of the object. So R represents the radius. And in the equation up above, if we make a substitution, instead of omega we write V over R, which is found from the equation at the bottom, then omega squared would be V squared over R squared, and those R's cancel, leaving us with 1/2 bmv squared. Maybe that manipulation will help you if you ever have to solve a conservation of energy equation or something like that. More qualitatively, here I have an inclined plane, and at the top of this inclined plane I have a solid sphere that is going to roll without slipping, and I have a block of ice that's going to slide down the plane without any friction at all. And I want you to think about what's going on with each of these objects. So first, the solid sphere is rolling without slipping. Let's think about what that means again. If something is rolling without slipping, then that means there has to be static friction between the object and the inclined plane. It means momentarily the object is rolling and the contact point with the surface is momentarily at rest. So there's an upwards frictional force that's exerted on this object. I want to go ahead and pause for a moment and draw this a little bit bigger. I want to draw the inclined plane and then the solid sphere more largely like that. And I want to show all the forces that are being exerted on this rotating solid sphere. So we've said that there's an upwards frictional force being exerted on the object, and that occurs at the contact point between the two surfaces there. This solid sphere also has some weight, and so there's a gravitational force that could be said to be exerted at the center of mass of the solid sphere, and so this force represents mg. And there is a normal force being exerted on this object. That normal force is exerted at the contact point between the sphere and the surface, and it's perpendicular to the surface like this. So those are the three forces that are exerted on the solid sphere as it rolls down the inclined plane. And what I want to remind you of is if that solid sphere is going to rotate down the inclined plane, then it's rotating. And if it's rotating, then that means there must be a torque exerted on that object, an unbalanced torque. And so which of these forces is providing the torque is what you should be thinking about. And if this object is rotating about its center, then any forces that are applied parallel to the axis of rotation, the center, would not be able to cause a torque. And so let's look at the normal force. The axis of rotation is at the center, and the normal force is directed exactly toward that axis of rotation. For that reason, the normal force cannot cause the object to rotate. The gravitational force is also directed along the line of the axis of rotation, but that's not the only reason why it doesn't cause a torque. The gravitational force does not cause a torque because this force is actually generated from the center of the object. Gravitational forces are said to be emanating from the center of mass of the object, and the center of mass is the axis of rotation. And so for that reason, not only is mg directed along the line where the axis of rotation is, but it actually originates and occurs at the axis of rotation. And I think you'd find it very difficult to try and open or close a door by applying a force to the hinges. And that's effectively what this is. A force applied at the axis of rotation can't cause rotation. I can't open a door by trying to open it from the hinges. So the only force that could cause a torque is the frictional force. And it does. And I want you to see this distance here, right? This yellow line that I'm drawing. The radius of the sphere, r, is the distance from the axis of rotation to the location where that frictional force is being applied, and that frictional force is exerting an unbalanced torque on the object. And due to that frictional force, the object is able to rotate, and as long as that static frictional force is present, it's able to do so without slipping. So because of that, the solid sphere rolls down without slipping. Now, the block of ice is much simpler, right? The block of ice is going to go down without any friction at all, and the only force that's exerted on that block of ice is the downward force of gravity. Well, the gravitational force points directly downwards, mg, and the component of the gravitational force that points down the ramp is mg sine theta. Now, that's not so important, but what I want you to remember is the reason why the block of ice wins. The block of ice gets down the ramp first, and why does it do that? Maybe I tell you that the dimensions of the block of ice and the dimensions of the sphere are the same. They're released from rest at the same height, and they have the same mass even. So all these quantities are the same. Why would the block of ice get down there before the rotating object does? we seem to have this intuition that if I released a block of wood and a marble from the top of a ramp, that certainly the marble would get to the bottom first. But in the case that I have a frictionless block that slides, it translates down the ramp, in a rotating object that not only rotates but translates down the ramp, the block of ice is always going to win, so long as that surface is frictionless. And I want to understand that by analyzing the conservation of energy equations that I could write for either one of these objects. So let's talk about the sphere first. It starts with an amount of potential energy equal to mgh, and as it rolls down that ramp, it translates. So it has to have some translational kinetic energy, but it also rotates. So it has to have some rotational kinetic energy. Now let's go down to the block of ice. It starts off with that same amount of gravitational potential energy, mgh, and it converts all of its energy into translational kinetic energy. And so the key difference here is some of the energy for the rotating sphere is used up to cause the rotation. But for the block of ice, all of its energy goes into translational kinetic energy. And so a misconception is that because the solid sphere is translating and rotating, it must now have more energy. But that's not possible, right, by conservation of energy. What's actually happening is not all of the gravitational potential energy gets converted into translational kinetic energy, because some of it is being used up to cause the rotation. Some of it is being used up, right? Think of taking that gravitational potential energy and putting it into these other two types of energies, like a basket, right? In the case of the block of ice, all of the energy gets to get put into that translational kinetic energy basket. But in the case of the rotating object, it has to deposit some of its energy into the translating and rotating of that object. For that reason, the block of ice wins because it only has to translate. The solid sphere loses because it has to translate and rotate. Some of its energy is lost due to the rotation. One of the last topics that we studied in rotation was the idea of angular momentum. And angular momentum was defined in a similar way to how we define linear momentum. For linear momentum, we said P equals mv. But now, instead of mass, I have moment of inertia, and instead of linear speed, I have an angular speed. And so we defined angular momentum as a quantity L that's equal to I times omega. And similar to the way that momentum is conserved, we can have conservation of angular momentum as well. As long as the net external torque on a system is equal to 0, the angular momentum will be conserved. And so for linear momentum, the net external force needed to be equal to 0. And for angular momentum, the net external torque needs to be equal to 0. And so hopefully you remember the demonstration where someone is spinning around on a rotational platform, and they're holding their arms in, and in each hand they're holding some weights. With their arms in, their angular speed omega is quite large. They're able to spin kind of quickly. And their moment of inertia is relatively small because they're holding their arms in with the mass inward. When they take their arms and they hold them as far out as they possibly can, their moment of inertia increases and their angular speed decreases. So we go from having a small moment of inertia, large angular speed, they're moving around quickly, to having a large moment of inertia and a smaller angular speed. They're moving around more slowly. And then, of course, if they pull their arms back in, they speed up and go faster. And in this case, since these rotating platforms tend to have a very small frictional torque, you can spin around pretty constantly. So we can say that the angular momentum is conserved. So Li equals L omega between these two cases that I've drawn. In fact, most conservation of angular momentum equations look something like this, where you're equating an initial and final case where the moment of inertia goes up and the angular speed goes down. Now that we've talked about all of these quantities, right, we know moment of inertia has units of kilograms times meters squared. We know that angular speed has units of radians per second squared. And so the units of angular momentum are the units of moment of inertia times the units of angular speed. So kilograms meters squared per second. And remember, the radians does not go into the final unit for angular momentum. And yes, angular momentum has an ugly unit, but it is what it is. The units of angular momentum are kilograms meters squared per second. When we studied linear momentum, we learned about something called impulse. We represented an impulse with the letter J. Okay, and we learned that if an object experiences an impulse, it experiences a change in momentum, delta p. So for linear momentum, what happens is if there is an external force that causes the linear momentum of a system to change, then we know that we can relate the change in momentum, delta p, to the average force exerted on the object over the time interval over which it occurs. Right? I exert an external force on an object and the momentum changes. And we can relate that as Pf minus Pi equals the average force times the time interval. And now, instead of a linear impulse due to an external force, now we're going to have an angular impulse due to an external torque. So an external torque causes the angular momentum of the system to change, delta L. And we can write this as Lf minus Li equals that external torque times the time interval. And so angular impulse, linear impulse. Examples of an angular impulse is really well, if we think back to that lab where we had that rotational motion apparatus, we had a piece of PVC pipe that looked something like this. And I want you to imagine this thing spinning around like it was in the lab. So it's spinning around with a certain angular speed omega. And the moment of inertia is constant because, we're not changing the size, shape, mass, or orientation of this relative to the axis of rotation. As that PVC assembly was rotating around with an angular speed, what we found is that there's actually and by the way, we had this thing hooked up to a table where there was some mass falling down, and the weight of that mass exerted a constant torque on this object. And so that thing caused it to move at a certain angular speed, but one of the things that we found is that between the contact point of the PVC and the stand that was holding it up, at this point, there was some friction between the PVC pipe and the stand, and that thing was causing a frictional torque to be exerted on the PVC assembly. And so in the same way that if I push an object across a table, it comes to rest because of friction, in a lot of cases, there is friction between the axle about which something is rotating and the object that's doing the rotating that slows it down. And so make sure you remember that there can be things like frictional torques that change the angular momentum or the angular speed of something. And lastly, I'd like to make the point that for linear quantities, we typically talk about something being in the positive direction or the negative direction, but we can't really do that for angular quantities. So in AP Physics 1, we say that objects are moving in the clockwise direction or the counterclockwise direction. And that's the way that we define angular quantities, and we can say that they're positive or negative based on that fact. And so a lot of times when we solve angular problems, we have to somewhere write a little angled line that means, well, I'm letting the clockwise things be positive, and so all the clockwise torques will be positive. The last slide that I have for you is a list of all the linear and translational stuff and the angular and rotational stuff. So positions are measured in x or y in meters, or they're measured in theta in radians for rotational quantities. We have linear speed in meters per second, angular speed in radians per second, linear acceleration in meters per second squared, angular acceleration in radians per second squared. In linear equations, we tend to only worry about the mass, which is measured in kilograms. And for rotational problems, we have to consider the moment of inertia, or the rotational inertia, which is b mr squared, some number times mr squared. For translational problems, we worry about forces measured in newtons. And for rotational problems, we worry about torques, which are measured in newton meters, the product of force and distance. Translational kinetic energy is equal to 1/2 mv squared, measured in joules. And rotational kinetic energy is equal to 1/2 I omega squared, and it is also measured in joules. And sometimes we write conservation of energy equations where rotational kinetic energy is just another term in that equation. There's no need to do anything separately there. It's just another form of energy. We have linear momentum, P equals mv, measured in kilograms meters per second, and angular momentum, I times omega, which is measured in kilograms meters squared per second. And then the two equations that we just mentioned, linear impulse and angular impulse. And lastly, as I said, linear or translational quantities are often described as having a positive or negative direction. And for rotational quantities, we need to describe directions as being clockwise or counterclockwise. However, I can't write into an equation something that's clockwise or counterclockwise. So the last thing I'll tell you is that if I have a rod that looks like this, and the axis of rotation is the center of that rod, and there's a couple of forces acting on that rod, maybe there's one this way, maybe there's one this way. Notice how those two forces point in the same direction. If we were writing a net force equation, we might call both of those forces negative because they both point downwards. But we need to be very careful about which direction those forces cause rotation. And so while those forces both point downwards, the torque generated by the force on the left would certainly cause the rod to rotate this way, which is counterclockwise. And the force on the right side, while it does still point downwards, would very much cause the rod to rotate this way, which is clockwise. And so in order to determine whether a torque should be positive or negative, you really have to figure out whether it's going to cause a clockwise or counterclockwise rotation. And the only way to do that is look at where the force is being applied relative to the axis of rotation. And so in this example, if I am defining clockwise rotations as being positive, then that means the force on the right would cause a positive torque, and the force on the left would cause a negative torque, despite the forces pointing in the same direction.